In this video, we are going to talk about capacitance, and in particular, we're going to basically take everything that we've been doing so far with electrostatics, and we're going to bring it all together into one meaningful idea with the capacitor. And so all the skills that we've learned up to this point, they all come to a convergence here in this topic. Now, a capacitor is just an electronic component which stores energy by separating charges in a circuit. Typically, the capacitor is going to be used in situations where you are looking to either smooth an electronic signal or you're looking to give a large burst of energy that would be otherwise difficult to accomplish if you were using only a battery. The only similarity between a capacitor and a battery, or the only meaningful similarity between the capacitor and the battery, is that they both store energy. But how they store that energy is very different. Batteries are storing the energy in a chemical reaction, or they're releasing energy through a chemical reaction. In the capacitor, it works more mechanically. You're literally physically moving charges from one location to another and then letting them move back again. So we're going to talk more about capacitors later whenever we get into circuits. And so I'm just going to, right now, just focus on the main ideas of the capacitor and what it is that we have to do. All right, so what constitutes a capacitor? Okay, it's an electronic component which can store charge. It basically separates the charge. So what exactly constitutes a capacitor? And most simply, a capacitor is going to be any two conductors that are a part of a circuit but isolated from each other. They constitute a capacitor. So what I mean by that is this: if you have a metal rod and two metal rods, and they're separated, but they're connected with a wire to a battery like this, you have a capacitor. It is an extremely small capacitor, and it's of almost no value considering the amount of capacitance that you would have there. But that does nonetheless constitute a capacitor. And so, in effect, everything in a circuit does have some capacitance. Now, the most common capacitor is the parallel plate capacitor. And the parallel plate capacitor you'll recognize because it really looks just like a miniature soup can. If you open up anything electronic, the parallel plate capacitors, they're round, they're cylindrical in shape, just like that. And really what's going on is on the inside, if we were to cut the top of the can off and just take everything out, basically what we have is a jelly roll of layers. And that's really what a parallel plate capacitor is. There'd be two layers there, separated by an insulator, two conducting layers separated by an insulator. All right, so our definition of capacitance, mathematical definition of capacitance, C. So C is defined by Q over delta V. All right, now, C is the capacitance. It has the units of farad, and that's a very large unit. The farad is 1 coulomb per volt. Okay, so typical values for capacitance are going to be nanofarads, which is 1 times 10 to the minus 9, and then microfarads, which is 1 times 10 to the minus 6 farads. These are going to be the most common, but they get larger and they do get smaller. Q is going to be the charge on one electrode. And this constitutes an electrode. The two conductors which have been separated electrically. So we're only looking at the charge on one electrode. And that's because the charge that's lost by one electrode, the electrons, they're going to move through the circuit. They're going to be deposited right back onto the other electrode. So we're only looking at the charge on one electrode. And then finally, delta V, this is the potential difference between the electrodes. All right. And if you have a fully charged capacitor, then the potential difference of the capacitor is equal to the potential difference of the battery. All right, now perhaps you can start to get the idea of what's going to happen here. You know, in the last series of videos, we were looking at calculating electric potential and potential difference. And that was also dependent on our ability to use Gauss's law or Coulomb's law effectively. And so that's what's happening here with capacitance. You can see it's all coming together with that delta V. Okay, so what we're going to do next is basically set up the basic model for how we go about doing our capacitor problems. And capacitor problems are extremely important for the AP exam. It's pretty much a guarantee that you're going to have to do a problem like this in some variety. And, you know, College Board, they're really good at coming up with new and interesting ways of creating these capacitor problems. So it's actually just really important that you understand the process of setting up a capacitor problem so that you can work through whatever twists they happen to throw into the problem. You don't want to be stumbling over the fundamentals of a capacitor problem. So it all starts with our definition. So we write C is equal to Q over delta V. And delta V is an unknown quantity here. Oh, and by the way, we just have a parallel plate capacitor. Remember that this is going to create a uniform field in between the two, and so you know, this is the simple case. And so in order to get delta V, we have to turn to either Gauss's law or Coulomb's law, and since we have basically an infinite plane, because we're so close to the surface, these plates would be very, very close together. We can use Gauss's law, so delta V is going to be equal to minus the integral of e dot ds. So this is what we use for the Gaussian symmetry, and that's going to be from A to B. And then lastly, just kind of following this through, to get E, we go to Gauss's law, and so the integral of E dot dA is equal to Q enclosed over epsilon naught. So finishing that Gauss's law, we have E times pi r squared is equal to sigma, the surface charge density, times the area enclosed by the Gaussian cylinder, which was pi r squared, and that's going to be divided by epsilon naught. Now, I'm not taking a lot of time to go through this again in all of its little details like we did in class. Okay, please understand that. You may end up taking more time on your own setting this up and getting through it, but you can go back to another video to get to that. All right, so the pi r squareds are going to cancel out, and that's going to leave us with E is equal to sigma over epsilon naught. And it's because R never shows up in this expression that we know that the electric field is going to be uniform whenever you have two parallel plates. So we substitute that expression into delta V, and so we get delta V is equal to minus the integral of sigma over epsilon naught ds, or dr, however you want to look at it. And this is going to go from A to B. And ds, remember, is going to go in the same direction that you're moving, so this is going to be our ds or dr. And because there is no length dimension showing up here, these are both constants, we can write delta V is equal to minus sigma over epsilon naught times the integral of dr from a to b. And we've already defined a variable for this, and that is that it's going to be d. It's going to be a length d. So what we end up with is delta V is equal to minus sigma over epsilon naught times d. Okay, so now we'll substitute that back up into our expression or our definition for capacitance. Remember, that's all we're doing. We're just defining what capacitance is here, just in terms of other variables, and we get C is equal to Q over a negative sigma over epsilon naught times D. All right, now we can move epsilon naught up into the numerator, so we get C is equal to Q over minus sigma D, and epsilon naught goes into the numerator. And now we get to rewrite sigma. Sigma is, so we get Q epsilon naught over sigma, which is charge per unit area, times D. We can cancel out the charge. A will go into the numerator. And so we get C is equal to epsilon naught A over D. Now, what this tells us conceptually is that the capacitance has absolutely nothing to do with how much charge is on the capacitor. Capacitance is like a property. The property that we're looking at is how much charge per volt. So let's take a look at just a simple example of what I'm talking about here with the, it's a property of the capacitor. If you have a capacitance is equal to 2 farads, then that means you're going to be storing 2 coulombs for every 1 volt of potential difference. 2 coulombs per volt. So if you apply 1 volt of potential difference to those plates, then you're going to store 2 coulombs of charge. If you apply 2 volts, then you're going to store 4 coulombs of charge. If you apply 3 volts difference, then you'll get 6 coulombs of charge. So how much charge is actually stored on the capacitor has nothing to do with the capacitance itself, in as much as the capacitor has physical limits that we'll talk about as we go throughout this part of our unit. You just can't fill a capacitor up indefinitely. So what this expression is really telling us is that capacitance is describing the electrodes. All right, capacitance is determined by the geometry of the electrodes. The geometry being how large are the electrodes, how far separated are the electrodes. That's what determines the capacitance.